Okay. So today we are going to have a problem solving session. Let us start it. A simple one. So let x1, x2, xn be IID random variables with probability xi greater than 0 is 1, non-negative random variable, and finite second order moment. Okay, then find the value of say x1 divided by sum over xi, I running from 1 to respectively. How to do it? So before we start, any guess? Okay. Any guess what will be the answer? Is the problem clear?
Yes, sir.
Before we start the proof, it will be nice if you can guess the answer.
Sir, 1 by n.
Okay,
Yes,
correct.
1 by n.
1 by n. So how to argue for that?
So if each of xi converges to x1, something like that, then it will become nx1.
No. How xi will converge to x1? Xi is itself is a random variable and not it is not a function of n. Suppose in particular, if you choose, say xi is our exponential distribution with parameter lambda, then what will be the distribution? For example, just set for example, if xi is a say exponential lambda, IID, then what will be the distribution of x1 by sum over xi? What will be the distribution of sum over xi? First,
Gamma.
gamma, correct. And x1 is exponential, that means gamma 1 lambda. So it should be beta 1 n minus 1. and its expectation will be 1 by 1 plus n minus 1 is 1 by n. So that is one particular case, but it has not said anything about the distribution. This thing is claiming in general with finite second order moment, non-negative random variable. Okay, so now let us see if you can argue in this way that expectation of sum over xi, I running from 1 to n, divided by sum over xi, I running from 1 to n. This is 1. Is it okay?
Yes,
Yes.
sir.
If it is so, then expectation of sum over xi divided by sum over xi. This is also 1. The same thing. Just this summation I have written outside. Now, let xi divided by sum over xi, I running from 1 to n. This is I am denoting as yi. And if I define yi equals to this, then yi's are identically distributed. Because xi's are IID. Here you have sum over xi, and here you have any xi. So whatever will be the distribution of x1 will be the same distribution of x2 will be the same distribution of will be the same distribution of x1 divided by sum over xi, x2 divided by sum over xi. So all of them will have the identical distribution. And as they will have identical distribution, they will have same mean. So it will be nothing but expectation of sum over yi that is equals to 1. So let expectation of yi equals to some constant c. And as they are identically distributed, then it is c times n equals to 1. That implies c equals to 1 upon n. As simple as that. Yi's need not be independent. That is the point. They are identically distributed. Yi's need not be independent. But they are identical. That's it. Okay. So new problem. Let's consider this one. Let x1, x2, x3 are IID normal 0, 1. Then find the distribution of u defined as x1 plus x2 plus x3 whole divided by x2 minus 2x1 plus x3 whole divided by root 2. Tell me, what will be this one? Okay, first try to guess what it will be. Okay, what will be the distribution of the numerator part?
Normal 0,3.
Correct. Normal 0,3. Denominator?
Normal 0,3.
Yes. Now, what you know from our previous lectures. So let us define this thing y1, y2. So if it is so, then y1 divided by root 3 follows normal 0, 1. y2 divided by root 3 follows normal 0, 1. Now, what more you can claim about it? So, what will be the, what more you can say? Are they independent? y1, y2?
No, sir, I think.
So how will you check whether they're independent or not?
The
Hello?
covariance can be 0 if they're independent.
Yes, so check for covariance of y1, y2. Check, it is -2 plus 1 plus 1 divided by root 2. Which is 0. Then what can you claim? y1 and y2 are independent. Only because they are normally distributed and covariance both. Okay. Now what can you say about this? What will be the distribution?
Cauchy.
Now, what can you say about this distribution of this
Cauchy
ratio?
distribution.
Say again.
Cauchy distribution.
Cauchy, right?
Yes, sir.
Cauchy 0, 1, or equivalently you can say it is T distribution with 1 degree of freedom. But as the construction is given here, it is more likely to call it cos. So normal 0, 1 needed, and at the same time their independence needed. Then the ratio of normal 0, 1 with independence will follow Cauchy distribution. Okay, so I'm giving another similar kind of problem, but it is something different. Okay, so let x1, x2, x3, x4, x5, x6 be IID normal 0, 1. Then find the distribution of V, which is x1, x2 plus into x3, x4 plus x5, x6 all divided by, say, x1 square plus x3 square plus x5 square. Bolo. All of these questions are very good questions for your any interview or comprehensive viva, this kind of thing. Nothing requires big calculation. Just it requires your understanding about the subject. What will be the answer now? This problem is even easier than the previous one. You have to identify what will be the result. Guess, first guess. What can be the answer?
So is it normal again?
Yes, normal again. You are perfectly all right. How?
Sir, it's just an intuition, like.
Okay, intuition, but intuition doesn't come from the.
Yeah, sir, like in the numerator we have square of normal order something, and in the
Yeah.
denominator we have like the power one. So somehow it will come out to be normal again.
Okay, so you have to argue it properly. So let us consider in this way, that if you consider that the conditional distribution of V given x1 equals to small x1, x3 equals to small x3, x5 equals to small x5. Okay, so V given x1, x3, x5 is following normal 0. So that means you make these three things constant, so as well as these three coefficient constant. So it will be following normal 0, 1 trivially, which is free from x1, x3, x5. Okay. So the joint distribution of V x1, x3, x5 is, say, f of V x1, x3, x5. Again, it is phi V, phi x1, phi x3, phi x5. Phi is the PDF of normal 0, 1. So phi t equals to e to the power minus half t square by root 2 pi. So if this is the joint density of this, then f v of v is f v x1, x3, x5 integrated with respect to x1, x3, x5, dx1, dx3, dx5, and you will be left with only this phi of v. That implies v follows.
So
As
can you
simple,
explain this? V given x1, x2, x3. Why is it free from
yeah,
x1, x2?
so say for example, if you choose x1 equals to say 1, x3 equals to 0.5, x5 equal to 0.79. So put the value x1, x1 that 0.5 into x2 plus 1 into x4 plus 0.75 into x6 divided by 1 square, 0.5 square, 0.75 square. So if so it is eventually becoming in this way that sum over ai, so x2i divided by sum over ai square. So not sorry, I plus 1. So here you can see that it is a linear combination of normal and scale it down by its variance. So it will be normal 0. And as it is normal 0, 1, you can see that there is no impact of individual xi here. So whatever value you choose for AIs, it will be always normal 0. So the conditional distribution of V given x1, x2, x5 is normal 0, 1, which has no impact of x1, x2, x1, x3, x5, whatever may be given, it will still follow normal 0, 1. And as a consequence, the joint distribution of this given, given the joint distribution of this is the conditional distribution multiplied by the marginals. So marginals, this x1, x3, x5 are IID. So their joint distribution is x1, phi of x1, phi of x3, phi of x5. So this is the conditional distribution. This is the marginal distribution. So this is the joint distribution. Now you got to get the joint distribution, integrate over these three marginals. You will get the marginal of E. That's it. Is it okay?
Okay.
Thank you. So So calculation is less, only understanding important. Okay. So as we are doing conditional, let me just do one more and give one homework. But again, this is a repetitive work, but you need to better to know. This result you know already. That let X be the number of trials required to get the first success. Required to get the first success in a sequence of IID Bernoulli random variables. Okay, then find the expectation of X. We have done it in our class. Do you remember what will be the result? So if probability of success is P, what will be the result? Number of trials required to get the first success.
1 by P?
1 by P. Okay. Now the same story you can, so we have usually done, we have defined the geometric in a different way, the number of trials preceding to the first success, then this quantity is 1 plus geometric, and then geometric has mean Q by P, so 1 plus Q by P is 1 by P. That way we have done. Well, that is all right. Even from the definition, you can calculate the expectation of this random variable. That is also all right. Now, today, let us try to see it in a different way. That, so expectation of X, let us define, say, Y. Y is the outcome of first trial. Okay, so Y can be success or failure. So Y is 1 if success, Y is 0 if failure. So expectation of X. So expectation of X you can compute in terms of conditional expectation of X given Y. So it is nothing but expectation with respect to Y, expectation of X given Y. Okay. So here you notice the thing that Y will be, first trial will be success with probability P, and failure with probability 1 minus P. If first trial is success, then what will be the expectation of X? Already it is given that the first trial is success. What will be expectation of X? X is the number of trial.
1 plus expectation of X.
No, look, first trial is success given, and X is the
1.
number of trials.
1, sir.
This is 1. And if first trial is failure, that means you have lost one trial and you are still looking for the first success. So this quantity is 1 plus expectation of X. So already you have lost one trial, first trial failure, plus from that point onwards you are looking for the first success. So it is 1 plus expectation of x. So now you just equate it.
So shouldn't that be expectation of x minus 1?
No, which one? So this is
Second.
conditional. No, how? So you have already lost one trial. And from that point onwards, given that one trial is lost, you are looking for the number of trials required for the first success.
Yes, sir.
So now you see that here you will have a very nice 1 into p plus 1 minus p into 1. So that is 1. And then 1 minus p into expectation of x. And here is expectation of x. So this is p into expectation of x. So as a consequence, expectation of x equals to 1 by p. Very simply, you can argue in a different way. But now I'm giving you an interesting homework that let y be the number of trials required to get k successive successes. That means 3 wickets consecutively, that means hat trick. This kind of thing, if k equals to 3. K successive successes. Okay. So then show that expectation of y. Can you guess what it could be?
One by p raised to power k.
No, it is sum over 1 by p to the power I running from 1. So hint is this: construct a recursive relation and use this one as a initial condition. Okay, so you try to do that k minus, say in general, say k minus 1 success you have, successive success you have got, and then you are looking for kth success. In that way, construct a recursive relation, and from there you will get this equation with initial expression. When k is 1, this is the expression. But in general, for any k, you will. So intuition sometimes can ditch you. You have to be a little bit more careful and
Sir,
yes, please.
can we construct the following by cases such as if the first trial is a failure, then it is same as finding the expectation of y after the first trial. If the
Yes.
first one trial is failure and then it's a success, then it's the same as that 2 plus expectation of y.
No. In that way, you don't start then. So you do conditioning on, say, sorry. I'm in class, I'll call you back. Sorry, wait. So do conditioning on that the number of trials required to get k-1 successive successes. So here we have done on first trial, but here you have to do that. Suppose you have got k successive success with certain random number, then you are looking for kth successive success. That means after k-1 successive success, if you get one failure, everything lost. But if you get another success, you will be done. Is it okay?
Yes, sir.
Yeah. So you have to do in that. Now let us go to a little bit of empirical CDF. Okay. Okay, so let us define in this way that let say x1, x2, xn, they are IID with CDF F, continuous. Assume F is continuous. Okay, and given data, okay, so no further. So define empirical CDF as Fnt is equal to 1 by n, sum over I running from 1 to n, I xi less than equals to t. So this is an indicator function. So IA equals to 1 if condition A holds, 0 otherwise. So this is just a binary thing. Fnt is defined in this way. So eventually Fnt computes the proportion of observation less or equal to t. So that's why it is known as the empirical CDF. Now, can you tell me this thing? What n times Fnt will follow? So n times Fnt is nothing but sum over I running from 1 to n, indicator xi less than equals to t. Can you tell me what will be the distribution of this expression? Hello? Very easy.
Sir, will it be something similar to the rth order statistics?
No, no, no. You see the expression, what does it mean? Xi's are IID F. You are just checking whether Xi is less than T or not. Each term by term, you are checking whether Xi is less than equals to T or not. If it is less than equals to T, you count 1, otherwise 0. So each of these terms are either 0 and 1. You have some of them. Can you relate to any known distribution? So what is the probability any Xi less than T?
Sir, is it binomial n comma ft?
Yes, it is binomial n comma ft. As simple as that. It is binomial n comma ft. Now if I define Tn equals to root n fnt minus ft divided by ft into 1 minus ft. So find the large sample distribution of Tn. Large sample distribution of Tn. What will it follow? Can you guess? So what is expectation of FNT? N times FNT follows binomial n
FT.
What is expectation of FNT?
FT.
Say again?
FT.
FT.
Yep. What is variance of FNT?
FT 1 minus FT. FT into 1 minus FT.
How? 1 minus ft. What is the variance of binomial NP?
Sir, ft 1 minus ft upon n.
Yes. Yeah. Okay. Now you look at this expression and tell me where this will go in distribution as n goes to infinity.
The normal 0, 1.
Yes. Tn converges in distribution to normal 0, 1 as n goes to infinity by CLT. And where Tn converges in probability as n goes to infinity. Sorry, not Tn, Fn. Fn converges in probability as n goes to infinity. Oh, Fn converges in probability to Fnt. Ft by Wick law of Lachman. You see, the mean of Fnt is Ft. Variance is going to 0 as n goes to infinity. Use Chebyshev inequality. It will converge to Ft by Wick law of large number. So this construction is a very important construction because it gives an interesting feature of this empirical CDF. So suppose your f is like this, smooth behavior of CDF function Ft, but Fnt, whatever you will have, it has a step function kind of nature. Or given the data, it will have a step function kind of nature. So this is Fnt. Black one is Ft and the blue one is Fnt. And now you see that the blue one, Fnt, is discontinuous. And not only that, it has the property of CDF. So right continuous, left function only. Right. But Ft is continuous. So ultimately it can be shown that Fnt will converge to Ft for all the points wherever Ft is continuous. This is one thing that can be shown, and it is also can be shown in this way that Fnt minus Ft, this supremum over T, that goes to 0 with probability 1. This thing will hold. And not only for each of the point, if you take for all T, if you take the supremum, then also it will go to 0. So it is a very strong result. And if you want to construct a testing we have not done, but okay, so if you want to construct a test based on root n Fnt minus Ft supremum over T, this can be used as a test statistic for testing whether the data are coming from FT or not. So, and such a test is known as Kolmogorov-Smirnov test. For CDF. So the problem is something like that. You are given a data set and it is told that the data are coming from a continuous distribution function, and you are asked to check whether the data are coming from, say, gamma distribution or not, or gamma with given parameter, gamma, alpha, beta known, that distribution or not, or it is coming from normal 0, 1 or not. So this kind of situation, we construct this kind of test statistic like this, and that test is more precisely known as the Kolmogorov-Smirnov test. And when the distribution is specified, so when distribution is specified, then we know specified as, say, F naught X. That means everything you know about the specified distribution for which you have to do testing. Then F naught of Xi will be following uniform 0, 1 when if the claim is true. That means if the data are truly coming from F naught, if you do F of Xi, it will follow uniform 0, 1. That we have already proved in our class. And then the test statistic will reduce to, supremum over T root n, I should say F naught n T in this way, minus T, which is said to follow Kolmogorov distribution or converge in Kolmogorov distribution for large. This distribution doesn't have a very good looking CDF. You will be able to see if you search for Kolmogorov distribution in internet, you will get it. So here it boils down to T because this follows uniform distribution, the CDF of uniform distribution of T, and here T is lying between 0 to 1. And F0 n T is the empirical CDF of F0 X. So you first do the transformation, then again use empirical CDF and the true CDF of uniform 0, 1, their difference scaled by root n, supremum of that over 0, 1 will converge to Kolmogorov distribution. So, and this is a very powerful, very useful test for continuous valued random variable to check whether the given data are coming from a particular distribution or not. So I'm leaving with one homework, which is not difficult, but you carefully handle it. So let x1, x2, xn are IID uniform 0, 1. Then find the covariance of root n fnt and root n fns. Fnt, fns are empirical CDF where t is less than s. Fine. Carefully do it. You will find something interesting. So, anything else?
So that f0 of f0 of xi goes to uniform 0 1. How that came up? Can you please say once?
Oh, you see. So for any random variable, f, so x is following f, where f is continuous. You define y equals to f of x. Do you remember what will it follow? So y definitely lies between 0 and 1 because it is probability. So probability y less than equals to small y equals to probability f of x less than equals to small y equals to probability x less than equals to f inverse y, because f is a continuous series of smooth function invertible. So that is f of f inverse of y, which is y. So probability y less than equals to y equals to y. That implies y follows uniform. We have done it in the class. Is it okay? Yeah.
Yes, sir.
Okay, so
can you show the question again?
Yes, please. x1, x2, xn, IID uniform 0, 1. So all those transformations are done. Right. Now you compute the covariance between root n fnt and root n fns, where t is less than s, so you can consider this also. You construct the fnt fns as from the definition, and from there you try to conclude. It will be easy two-line job. So from tomorrow we will study the statistics portion. Estimation we will start. Okay, see you tomorrow early morning. Thank you.
Sir.